Hi, I'm Nick Marino.
I'm Danica, Remmel.
Lagace.
I'm Jake Magee, and our project is an automated sauce mixer.
Cooking 3 gallons of pasta sauce from scratch requires an all-day commitment because the sauce must be stirred every 15 minutes to prevent burning at the bottom of the pot. This team's automated mixer makes cooking of all-day sauce possible without slaving over a stove by constantly agitating the mixture to prevent burning. A rendering is shown of the prototype mixer assembly. Sauce is sucked in through the top port of the screw pump and expelled out the lower ports. Here is a rendering of the mixer placed in a large pot measuring 11.5 inches in diameter and 8 inches deep. The pump cover releases from the lid with a counterclockwise turn. The auger can then be unthreaded from the drive mechanism, allowing both components to be easily cleaned. Pictured is a close-up of how the auger inserts into the drive assembly and threads into the drive shaft.
To start our QFD analysis, we identified home cooks as our prime customers. A home cook was then interviewed to determine the customer requirements. Those requirements were then evaluated and given a weighting. We looked for similar products already available on the market and then evaluated them with respect to our requirements. We determined the functional requirements of our mixer and related them to the customer requirements to decide on target specifications. The functional requirements were then related to each other.
When fully assembled, this is how the mixer will look in the pot. The clamps on the lid provide support for the mixer and help ensure the mixer is fixed to the pot. When the motor is activated, the motor's torque drives the shaft, which provides motion to the auger. The gears shown provide a 2-to-1 speed ratio from the motor to the auger. As the auger rotates, the fluid from the pot is fed to the top of the auger housing and expelled through the bottom back into the pot. For this analysis, the shaft of the mixer was observed. This shaft is used to translate rotational force from the motor to the mixer. This is a commercially available shaft made out of 1566 carbon steel. From the distributor, the following assumptions were made to help perform calculations on the shaft. Given the equations from the machine design book, it was able to be determined that the shaft safety factor for this mixer was 12.8. In this analysis, the bearings for the mixers were observed. The bearings are used to help facilitate smooth rotational motion from the shaft. These are oil-embedded ball bearings which are commercially available. For this analysis, the following assumptions were made. The machine design book for this course was used to assist in calculating the bearing life for this mixer. From the calculations, it was determined that the bearings used have an estimated run life of 49,580 working hours.
A bending and surface contact stress analysis was performed on the 90-degree bevel gear set that transmits power from the input shaft to the auger output shaft of the mixer. A commercially available gear set that provides a 2-to-1 mechanical advantage was chosen for the sauce mixer prototype, and the listed assumptions were used to calculate the results. The safety factor against bending was determined to be 3.1 for the pinion teeth. A contact safety factor of 2.0 was also calculated for the pinion.
A SolidWorks FEA was conducted on the helical screw to determine the location of any stress concentrations. We determined that the blade shaft interface had a high stress concentration and adjusted the fillet radii as needed. The analysis ran using a fixed boundary condition, the green arrows, and a constant 20 psi pressure load on the bottom surface of the blades. Here the colors represent the local von Mises stresses. On the right, the area in red shows where the factor of safety might be less than 1. This is not the actual loading, however, since the shaft will be mounted inside a bearing at that location. Next, we ran a SolidWorks flow simulation using water as the fluid and rotated the shaft 25 radians per second. The boundary conditions were environment pressure at the roof, inlet mass flow rates at the 4 cylindrical ports, and exit mass flow rates at the 6 rectangular exit ports. The instantaneous fluid velocity is represented by vector arrows, and velocity streamlines were added for visual effect. Assuming that the simulation results match reality, the fluid does seem to behave as anticipated, and the design could meet our minimum fluid stagnation goals.